Welcome back to the Deep Dive. We take your most crucial sources, articles, research, maybe even your own notes, and we really boil them down to the absolute essentials. We're here to give you that shortcut to being genuinely well-informed with hopefully some surprising facts and just enough conversation to keep you with us. Today, we're diving headfirst into something that's buzzing everywhere, but often feels, well, a bit foggy. Actually mastering generative AI within the enterprise. We've all seen the cool demos, felt that excitement, right? But here's the real question, the hard part. How do organizations actually get from a neat little proof of concept to a system that's robust, reliable, and ready for production? Our research makes it really clear. Implementing generative AI in enterprise environments, well, it represents one of the most challenging yet rewarding technical endeavors facing technology leaders today. And this is, just deploying another piece of software. It needs a fundamentally different way of thinking about architecture, about operations, governance, the whole lot. So our mission in this deep dive,
it's to unpack these battle-tested strategies, the things that have actually worked in real enterprise settings, to help you navigate this pretty complex landscape. The goal, help you unlock those significant competitive advantages, and really importantly, avoid the costly setbacks and, frankly, underwhelming results that lots of folks have run into.
Yeah, and what's fascinating, I think, is that the initial excitement, it's almost overwhelming sometimes, right? This buzz around GenAI often completely overshadows the really intricate, the multifaceted work that's needed to make it truly effective or crucially secure inside a business. We're not just talking about installing a new app here. This is really a transformation. It's about weaving this powerful new capability right into the core of how an organization works. So throughout this deep dive, we're going to map out that whole journey, starting with building those really solid strategic foundations, then getting into the nitty-gritty of the technical architecture, understanding why data strategy is just so critical, shoring up security a huge piece, and finally, managing these complex systems day in, day out in a demanding production environment. It's really a holistic view we need to take, looking at every single layer of complexity you're likely to face.
Okay, so let's unpack that. When organizations first start experimenting with GenAI, where do they typically stumble? What's the big mistake our sources keep pointing to? And what's the absolute first step for actually achieving long-term success? Because it sounds like there's a pretty common pitfall.
You're spot on. And that common pitfall, it's surprisingly persistent, actually. The most critical mistake, the one our sources really hammer home, is treating GenAI as a traditional software deployment, rather than recognizing it as a complex system requiring dedicated resources, governance, and continuous optimization. I mean, think about it like this, maybe. Traditional software, it's like a carefully engineered machine, right? You build it, deploy it, and mostly it does what you told it to do. Pretty predictable. GenAI, though, it's more like a living system, maybe even a learning organism in a way. It's dynamic, it can change, it can behave in ways you didn't quite expect if you don't, nurture and manage it properly. And when organizations underestimate that complexity, which happens a lot, they just don't allocate enough specialized resources. They don't set up the right governance from the get-go. And they definitely don't plan for the continuous tweaking, the optimization these systems absolutely demand. They might get a proof of concept looking great in a lab, but scaling that up, making it reliable, accurate, secure in a real tough production environment. That often becomes this huge, unexpected hurdle. It's a fundamental misunderstanding, really, of what this technology is.
Right, so it's not just getting the code right. It's a whole new way of operating, almost a philosophical shift. And you mentioned that first step for long-term success. Our sources call it defining specific, measurable business objectives. How is that really different from just saying, hey, we want to use AI to be more innovative?
Oh, it's vastly different because it moves you from these sort of vague hopes into concrete, actual goals. The cornerstone, the absolute foundation of any successful GenAI project is exactly that, defining specific, measurable business problems that the AI is going to tackle. Organizations shouldn't be chasing AI just because it's the new shiny thing or, to look innovative. It has to solve something real. Instead, the technology experts, they have to work really closely, hand in glove, with the business stakeholders to identify objectives like, say, improving customer satisfaction scores by 30%, or maybe reducing the time it takes to process manual content and legal by 50%. These aren't just nice ideas. They are, as the sources put it, both motivation and validation criteria. They give you a clear target, something concrete to aim for. They give you a quantifiable way to know if you succeeded, and a solid reason for making the investment in the first place. Without those clear, measurable goals, you risk building something technically amazing, maybe even groundbreaking, but ultimately it doesn't solve a core business need, or the business just doesn't see the value. It keeps the project grounded in real-world value right from the start.
That makes a huge amount of sense, tying it to tangible value. So, okay, you got those measurable business objectives locked down. How do the technical teams then translate those goals into a plan, an actual roadmap that also realistically acknowledges where GenAI technology is today? Because let's face it, there's often a gap between the business wish list and what the tech can actually deliver right now.
Exactly, and bridging that gap is crucial. This is where having a detailed roadmap is absolutely essential. It requires a really deep technical understanding of what these GenAI systems can realistically pull off in their current state, not just based on the hype or the latest headlines. This means doing an honest, sometimes brutally honest, assessment of the current model limitations. Because, let's be clear, no model is perfect, right? They all have blind spots, things they aren't good at. Plus, you need a clear view of the infrastructure needed to support what you want to do. Those GPUs, the data pipelines, it all adds up. And critically, it means setting realistic timelines for different levels of capability. You can't just promise a fully autonomous, all-singing, all-dancing AI agent on day one. That's just not how it works. The roadmap needs to clearly show how each piece of the implementation, from the initial data prep all the way to deploying and refining the model, actually brings measurable value along the way. It's about breaking down that big vision into smaller, achievable, value-adding steps. This really helps manage expectations across the whole organization and keeps the support coming for what's going to be, let's be honest, a multi-stage journey.
And executing that roadmap, our sources are really emphatic about needing an essential cross-functional team. This isn't just throwing a couple developers at the problem, is it? It sounds more like assembling a kind of AI dream team.
You absolutely do. Yeah, it's not at all like your typical software project. GenAI success demands collaboration across so many different disciplines, groups that, frankly, often don't need to coordinate this closely on traditional projects. It's like building an ecosystem of specialized expertise. So, for instance, you absolutely need data scientists. They bring that deep statistical and algorithmic knowledge, essential for picking the right models, optimizing them, understanding the subtle ways these complex systems behave. Then you have your domain experts. These people are absolutely critical. They provide the business context. They ensure the AI's output isn't just technically correct, but actually relevant, accurate, and useful for the specific industry or department or problem you're trying to solve. Your ML engineers, they're the backbone, really. They handle the complex infrastructure, the unique operational needs specific to AI systems. They make sure everything runs smoothly, efficiently, and crucially at scale. And in this landscape, cybersecurity professionals are just vital because Gen AI brings totally new attack vectors, new data protection challenges that your traditional security setups might just miss entirely. Think about things like prompt injection, where someone tries to trick the model, or data leakage, where sensitive info might accidentally slip into the AI's responses.
That's a massive point right there, especially with all the sensitive data enterprises deal with. It totally changes the whole threat landscape.
It really does. And the team, it doesn't stop there. You now need legal advisors as key partners. They help navigate the constantly shifting regulatory environment, not to mention the really tricky intellectual property issues around training models on proprietary data or generating new content. Is that output yours? Who owns it? These are big questions. And finally, but so importantly, end users. They give you the practical, real-world feedback that turns a theoretical capability into actual value. They're the ones using it day to day. Their insights on usability, on where it fails, are just invaluable for making it better over time. The key to making this diverse group work together, it's communication. Constant, effective communication. Regular cross-functional meetings, shared ways of documenting things, even developing a common language across these different fields. It all helps bridge those knowledge gaps. This kind of holistic, collaborative approach, it catches potential problems early on. And it's especially valuable when you hit those inevitable, often unexpected bumps during production deployment. It's really about creating a shared understanding that goes beyond just individual job titles.
Okay, this is where it gets really interesting for me. The architecture. Because the choices you make here early on can literally set you up for success or send you down a really expensive dead end. Our sources say these early decisions have a huge impact on system performance, scalability, operational complexity, cost, complexity, and time to deployment.
Wow. Okay, so what are the key architectural patterns you need to be aware of when you're thinking about bringing Gen AI into your business?
Yeah, this is absolutely foundational. Getting this right up front saves just a world of pain down the line. The first pattern, and it's often the easiest way to start exploring, is prompt engineering. This is all about carefully crafting and tweaking the prompts, the instructions or questions you feed the AI to get better, more accurate, or just more useful answers. And you do this without actually changing the underlying large language model itself.
So you're basically learning how to talk to the AI better, figuring out the best way to ask the question to get the answer you need, like learning its language. Exactly, that's a great way to put it. The big advantage here: minimal investment in infrastructure. You can often start really quickly just using an API. And you can get some surprisingly quick wins for specific, well-defined tasks. But the downsides are significant, especially for enterprise use. It offers pretty limited performance boosts for really complex, domain-specific stuff. And you have very little control over the consistency of the model's output, which can be a major headache in a business context where reliability is key. So it's a good starting point for experimentation, maybe, but it probably won't get you where you need to be for serious mission-critical applications.
Okay, moving up in complexity and capability, we get to the pattern that's really emerged as, well, the optimal starting point and kind of the workhorse for most enterprise implementations: retrieval augmented generation, or RAG.
Ah, SHA-RAG. Yeah, we hear that acronym. What makes it so effective, particularly for businesses? So, RAG systems, essentially, they combine the broad general knowledge that's baked into a large language model with specific, current, and often private information that's stored in your organization's own internal systems, databases, document repositories, knowledge bases, that kind of thing. Here's basically how it works. You ask a question. The system first goes and looks up relevant info from your private curated knowledge base, like a super fast librarian finding the right pages. Then it takes that retrieved, hopefully fact-checked information and uses that context to help the large language model formulate a much better, more accurate answer. Our sources indicate this approach can deliver 30–50% performance increases in domain-specific accuracy while maintaining cost efficiency. That's a big jump, and it directly tackles two of the biggest problems with base LLMs: their knowledge cutoff date. They only know things up to when they were trained, and their complete lack of knowledge about your specific internal company stuff. RAG bridges that gap. It makes the AI both generally smart and specifically relevant to your business. It's like giving the AI a custom, constantly updated library that only your company gets to use.
That sounds like a real game changer, especially for businesses needing to use their own current internal data securely. But what if you need the AI to really understand or talk in a very specific way? Maybe adopting your company's unique brand voice or understanding really niche industry jargon. Does RA handle that?
That's a great question, and that's where the next pattern fine-tuning comes in. RA is great for knowledge. Fine-tuning is more about behavior and style. Fine-tuning adapts an existing general-purpose model using your own organization's specific data. You're essentially teaching the model your company's specific language, the jargon, the preferred communication style, the nuances of your business context, maybe even how you handle sentiment. This creates a specialized version of the model that feels much more native to how your organization operates. The big pro: you can get substantial performance improvements in understanding domain terminology and matching your desired communication style. It can make the AI's responses feel truly integrated, not generic. However, fine-tuning is definitely more resource-intensive than prompt engineering or even RA. You need a good amount of high-quality training data that actually reflects the behavior you want to teach it. And you need the technical resources, the expertise, to manage that complex training process. It's a significant step up in terms of commitment and investment compared to RA.
Okay, fine-tuning sounds like a serious undertaking. But is there an even more intensive level? Or are companies often maybe mixing and matching these approaches for really complex problems?
That's a really sharp observation. Yes, to both. For the absolute most demanding, really unique requirements, there's pre-training. This means building completely new models essentially from scratch, usually for highly specialized domains where existing models just don't cut it, or where the data is so sensitive you absolutely cannot let it leave your control. The pro is ultimate control and capability for unique needs. The cons, though, are huge. It requires significant computational resources, specialized expertise, and substantial time investments. We're talking massive undertakings, typically only feasible for very large organizations with extremely unique needs and, frankly, very deep pockets. Think advanced scientific research, maybe certain intelligence applications. And then, yes, you absolutely see hybrid approaches. This really captures the state-of-the-art in advanced GenAI architecture. You combine multiple patterns to get the best of all worlds for complex situations. So, for example, you might use RAG to pull in the specific, up-to-date facts from your internal knowledge base, but then use a fine-tuned model to generate the response, ensuring it not only uses the correct facts, but also delivers them in your company's specific tone and style. The upside: These combinations can deliver genuinely superior performance by stacking the strengths of each pattern. The downside, naturally, is added complexity architecturally and operationally. Managing multiple interacting AI systems, each with its own data needs and update cycles, it's just inherently more challenging. So the key takeaway here, and it's worth repeating, is why ARG generally represents that sweet spot, that optimal balance between performance improvement and implementation complexity for most enterprises starting out. It gives you a powerful way to make general models smart about your specific business context and data without the huge investment needed for heavy fine-tuning or pre-training. It's often the quickest, most efficient path to seeing real business value.
Okay, so let's follow that thread. We've got our architecture, maybe leaning towards RIG. What does all this mean for the actual data you feed these systems? Because my gut tells me it's not as simple as just pointing it at your company SharePoint and letting it loose, right? It sounds like data quality becomes, well, not just important, but absolutely make or break.
You've absolutely nailed it. It's one of the most critical factors, and honestly, it's often the unsung hero or the hidden villain of GenAI success. Our sources really stress this. GenAI systems exhibit extreme sensitivity to data quality, and that poor quality inputs lead directly to inaccurate outputs, biased responses, and unreliable system behavior. What people often miss is that GenAI doesn't just reflect bad data, it actively amplifies it. A subtle bias in your data, a small error, an outdated policy document in your knowledge base, these can lead the system to confidently hallucinate completely false yet totally plausible sounding answers. This isn't just a small glitch. It can completely undermine your GenAI initiative. It erodes user trust, potentially leads to bad business decisions. It's huge. So data quality isn't just important, it's a core risk management discipline for AI.
So data quality isn't just important, it's like exponentially more important than for traditional software. With traditional stuff, bad data might cause a report to be wrong, which is bad. But here, it could lead to the AI confidently telling lies.
Exactly. The bar for data quality with GenAI is just much, much higher than for traditional applications, both in scope and how specific you need to be. Traditional databases, they can often cope with a bit of inconsistency, some missing fields. GenAI systems, though, they take those flaws and magnify them into confident-sounding but utterly wrong or misleading responses. Imagine a customer service bot giving confidently incorrect advice because of a few bad entries in its R knowledge base, or a legal research tool generating flawed summaries based on outdated case law it ingested. The potential damage is significant. This amplification effect makes investing in really comprehensive, meticulous data collection and pre-processing absolutely non-negotiable. We're talking about systematically rooting out errors, getting rid of duplicates, removing irrelevant junk before it ever gets near the model. It's about turning raw, messy data into high-fidelity fuel for the AI.
And it's not just about cleaning the data you have, is it? Our sources also emphasize dataset diversity. Why is that so crucial for making a GenAI system truly robust and reliable in the real world?
Yeah, diversity is equally critical. If you train a model or even build a R knowledge base using data that's too narrow, too homogeneous, or unbalanced, that system will inevitably struggle when it hits the real world. It just won't be able to handle the full variety of situations, user inputs, or audiences it encounters. If your training data, for example, only reflects one type of customer interaction or one linguistic style, or only historical data from one region, your AI is likely going to show bias. Or it'll just perform poorly when faced with anything outside that narrow experience. This need for diversity goes way beyond just simple demographics. It includes capturing a wide range of linguistic patterns, different ways people ask questions, all the relevant domain-specific terminology, critical edge cases, those unusual situations, and really covering the full spectrum of use cases the system is likely to face. A truly effective GenAI system needs to understand the rich, varied, messy context of its actual operating environment. And that understanding comes directly from having diverse, high-quality, representative data to learn from or retrieve. It builds resilience against unexpected inputs. And what's really fascinating here, and maybe a bit daunting, is how much success depends on continuous systematic management, not just a one-time data cleanup project. You simply cannot clean your data once and expect it to stay perfect forever. This brings us squarely to robust data governance protocols. These really form the operational backbone, the ongoing maintenance plan for successful GenAI implementations. These aren't just, bureaucratic policies sitting on a shelf. They have to be living, evolving systems.
So what do these robust governance protocols actually look like in practice for GenAI? What are the key pieces you need to have in place?
They need to cover several key areas, and often much more rigorously than for traditional data systems. First, you need strong validation processes. These check the accuracy and completeness of your data as it enters the system, as it gets transformed, and before it's used by the AI. Are the fields correct? Does this information make logical sense in context? Second, you need rigorous cleansing procedures. These are about systematically finding and fixing errors, things like duplicate records, incorrect labels, inconsistent date formats, even subtle ambiguities in text that could confuse the AI. And third, critically, you must have regular update mechanisms. These keep your data sets current and relevant. Your business changes, the world changes, regulations change. Your AI's knowledge base needs to keep pace, constantly refreshing with fresh, verified information. Stale data leads to stale, or worse, incorrect AI outputs. Our sources also really emphasize the indispensable role of automated data quality management tools. Especially at enterprise scale, manual checks just can't keep up with the sheer volume and speed of data updates. These tools need to be sophisticated enough to detect a whole range of issues: formatting problems, missing values, statistical outliers, duplicates, even subtle shifts in meaning or relevance over time. And crucially, they need to provide clear, actionable reports on data quality metrics, so you can track trends, jump on issues proactively, and actually demonstrate that your data's health is improving. It's like having an always-on diagnostic system for your AI's most vital input.
That's a really powerful concept. And I can easily imagine for certain industries, finance, healthcare, manufacturing, this is just a nice to have. It's absolutely essential, right?
Oh, absolutely. For those highly regulated industries, where, as one source noted, something like 98% of organizations report facing data quality issues, these governance protocols are completely critical. The stakes are just incredibly high. Inaccurate data could impact patient safety, lead to huge financial compliance failures, or cause major operational disruptions. On top of that, the regulatory requirements themselves, GDPR, IPA, various financial regs, often mandate detailed audit trails. You need to be able to prove where your data came from, how it was transformed, and what quality checks were applied. This adds significant layers of complexity, yes, but it's absolutely non-negotiable for maintaining trust, ensuring ethical AI use, and frankly, avoiding massive fines and reputational damage. It's about building verifiable trust in every single output the AI generates.
Okay, right. So we've got our strategy locked down. We've thought through the architecture. Our data is pristine and under constant governance. Now, the big question, where do we actually run this thing? Because deployment, it seems, is definitely not a one-size-fits-all deal. Our sources are clear. Your deployment choice hits everything: system performance, security, cost, and operational complexity. So what are the main deployment approaches you should be thinking about?
You're right. The deployment decision is far from simple, and it has really long-term implications. There are basically four main paths people take, each with its own set of pros and cons. The first is on-premises deployment. This is where you host absolutely everything: the models, the data, the inference engines on your own servers, inside your own data centers. You control the whole stack.
That definitely sounds like it gives you the maximum amount of control.
It absolutely does. The biggest pros are maximum security and really granular control over both your data and how the model inference actually happens. This makes it super attractive for organizations handling extremely sensitive information, proprietary IP, or operating in heavily regulated sectors where things like data sovereignty or physical control are absolute must-haves. But the cons are pretty significant too. There's a substantial upfront investment needed for specialized hardware. Those GPUs aren't cheap. You need deep, ongoing infrastructure management expertise right there on your own team. And it can limit your ability to quickly access the very latest model improvements or capabilities, which often hit the big cloud platforms first. You basically become responsible for maintaining everything, soup to nuts. Okay, next up, there's private cloud deployment. This tries to strike a balance, landing somewhere between the full control of on-prem and the scalability of the public cloud. You get dedicated infrastructure, meaning your resources are isolated from other customers, often hosted within a cloud provider's data center. But crucially, you also get to leverage the cloud provider's expertise in managing that complex AI infrastructure and specialized services. This route typically offers better performance and stronger security boundaries than sharing resources in the public cloud, while taking some of that heavy infrastructure management burden off your shoulders.
So kind of the best of both worlds, maybe. A dedicated feel, but with someone else managing the tricky hardware bits.
Exactly, that's the idea. Then you have hybrid cloud deployment. This approach is really all about flexibility, especially when you have different types of workloads with different sensitivity levels. You might keep your most sensitive operations where your crown jewel data is being processed by the AI running in your private cloud or even on-prem for maximum security. But then you could use public cloud services for things like development and testing, maybe less sensitive applications, or for handling sudden bursts of high-volume, non-critical AI tasks. This approach lets you optimize for both cost and security, giving you agility where it makes sense. The main downside, it requires pretty sophisticated orchestration and management tools and skills to seamlessly integrate and secure these different environments. Managing that hybrid complexity is a job in itself. And finally, the fourth option, public cloud deployment. This generally offers the fastest path to getting something up and running, usually with the lowest initial cost. You get immediate access to state-of-the-art models, pre-trained APIs, cutting-edge hardware, all without needing a big upfront capital investment. It's fantastic for rapid prototyping, testing ideas, and scaling up quickly if something takes off. However, this approach often comes with significant concerns around data security, the potential for vendor lock-in, making it hard to switch providers later, and challenges in predicting long-term costs. That pay-as-you-go model is flexible, sure, but costs can escalate very quickly if usage grows unexpectedly or if you're not constantly monitoring and optimizing. Especially for high-volume AI tasks, those bills can get scary fast.
Okay, that's a lot to weigh. So beyond just the technical pros and cons of the infrastructure itself, is there a core guiding principle you should use to make these critical deployment choices? And how do costs really factor in, especially in such a dynamic environment where usage might spike unpredictably? Because managing that budget seems like a real potential minefield.
There is a fundamental principle, and our sources really hammer this home. It should guide all your deployment thinking, and it's elegantly simple. Never host GenAI systems where you would not store the data they process. This forces you to maintain consistent security standards across your AI systems and your traditional data storage. It prevents creating weak links or accidental exposures. If your policy says your most sensitive customer data can never live in the public cloud, then you absolutely should not be processing that data with a GenAI model deployed there either. It ties your AI security directly to your established data security policies, simplifying a really complex decision down to a core compliance and risk principle. Now, regarding cost and performance optimization, it's a continuous balancing act. It involves juggling multiple factors that interact in really complex ways. For instance, the choice between just using commercial LLM APIs versus hosting open source models yourself, either on-prem or in a private cloud, that's a fundamental trade-off. It's deployment speed versus long-term cost control. API approaches get you started fast with minimal infrastructure hassle. But those costs, they can absolutely balloon with usage, especially for applications that make lots and lots of calls. You really need to project your usage carefully and understand the per token or per call economics inside out. Hosting yourself requires more upfront effort and expertise, but can be significantly cheaper in the long run for high-volume scenarios.
And what about the models themselves? You mentioned open source versus proprietary. That sounds like another big lever you can pull, both for cost and control.
It's another absolutely critical decision point. And the landscape here is changing incredibly fast. Open source models, from places like Hugging Face, Meta's Llama models, Mistral, etc., they now offer extremely high quality. In many cases, they rival or even outperform the big proprietary models for specific tasks. They can be much more cost-effective for inference workloads, especially if you're running them on your own optimized hardware. They give you much greater control over the model's behavior, how it's fine-tuned, how it's secured, and crucially, they help you avoid vendor lock-in. You have more transparency, more flexibility, often a huge community providing support and new techniques. However, proprietary models, usually from the major cloud providers or players like OpenAI or Anthropic, they might offer specific advantages too. Perhaps better performance on certain highly specialized tasks, or maybe more robust commercial support agreements and managed services that can significantly reduce your operational burden. That managed aspect is a really valuable consideration for many enterprises that don't want to build deep in-house AI ops teams. And finally, don't forget model size optimization. This is all about recognizing that you don't always need the biggest, most powerful model for every single task. Smaller, more specialized models might lack the encyclopedic knowledge of the giant ones, but they can be incredibly effective and much, much cheaper to run for specific, well-defined jobs. The key idea is resist the urge to just deploy the largest model available for everything. Instead, carefully match the model's capabilities and its cost profile to the actual requirements of the task. A smaller, maybe fine-tuned model could handle summarizing internal meeting notes or classifying customer support tickets just as well, if not better, than a massive general-purpose model, and do it at a fraction of the inference costs and using far fewer computational resources. It's about being smart and efficient with your AI resource allocation.
Okay, it makes sense. So let's say we've made our choices, the system is deployed. But the job is definitely not over then, is it? We need to keep these systems running well, performing accurately, securely, cost-effectively. And that means specialized monitoring, something that goes way beyond traditional software metrics. Our sources are very clear. GenAI systems need specialized monitoring and operational practices, capturing both technical performance and output quality. What are some of these key performance indicators that are so different from what ops teams might be used to?
Yeah, this is a huge shift and a major area where traditional IT operations teams really need to upskill or adapt. For GenAI, you absolutely need to track indicators that reflect the unique, often probabilistic and variable nature of these models. For example, instead of just looking at average response times, you need to rigorously track latency consistency. GenAI apps often have really high variance in how long they take to respond, depending on things like how complex the prompt is, how much context you provide, the specific model architecture. A consistently slow response is one kind of problem, but wildly unpredictable response times can be way more disruptive and frustrating for users, often leading them to just give up. Then there's throughput stability. How many requests can the system handle reliably over time? This is critical for maintaining a smooth user experience, especially under varying load conditions. You need continuous monitoring to ensure performance stays stable even when demand fluctuates, which it inevitably will. Users expect consistency. And finally, you need to carefully track resource utilization patterns, not just average CPU or memory usage. GenAI workloads can suddenly exhibit these dramatic spikes in demand for memory or compute power that traditional capacity planning, based on averages, might completely miss or fail to handle gracefully. You need monitoring and alerting systems that can catch these bursts and potentially trigger auto-scaling before they impact performance.
What's really fascinating here, though, is moving beyond just the technical numbers, latency, throughput, CPU, to actually assessing the quality of what these systems are producing. That seems inherently more complex, more nuanced, maybe even subjective, compared to just checking if a database query returned the right number of rows, for instance. How do we even begin to measure that effectively and systematically?
That's exactly where the really unique quality metrics come into play. And honestly, it often requires a smart blend of automated techniques and human evaluation. For instance, measuring hallucination rates is absolutely critical. Remember, this is when the AI confidently spits out information that sounds plausible but is factually wrong or just completely made up. Measuring this systematically isn't easy. It requires sophisticated techniques like comparing the AI's generated content against a database of verified, trusted facts, or implementing workflows where human reviewers sample and rate the factuality of outputs. Then you have accuracy scores. These need to somehow capture the subjective nature of language. Is the answer not just factually correct, but also relevant, helpful, well-phrased, while still providing quantitative measures that you can track over time and use for automated monitoring and alerting. It's a tough balance, finding metrics that reflect nuance but are still measurable, and crucially, bias measurements. You need ongoing systematic evaluation to check for unfair or discriminatory behavior across different demographic groups or different types of use cases. You have to actively look for biases related to gender, race, age, etc. to ensure your AI isn't accidentally perpetuating or even amplifying harmful societal biases that might have been present in its training data. This requires careful design of test sets and evaluation protocols. Beyond those core quality metrics, you absolutely need to track user experience metrics. These give you crucial feedback on how effective the system actually is in the real world, from the user's perspective. Are users able to successfully complete the tasks they came to do using the AI? That's your task completion rate. Are they satisfied with the interaction and the results? That's your satisfaction indicators, often captured through simple thumbs up, thumbs down ratings, short surveys, or feedback comments. And things like retry patterns. How often do users have to rephrase their prompt or try asking the question again in a different way? These can be incredibly powerful indicators of underlying problems. If users are constantly struggling to get the right answer, something fundamental isn't working well, regardless of what your technical latency metrics might say. It reveals friction and failure modes.
And managing the costs, which we touched on earlier, that absolutely has to be an integral part of production operations too, right? This isn't a set it and forget it kind of billing, I imagine.
Not at all. Granular cost metrics are completely essential because GenAI systems, especially those using APIs, often have complex cost structures that vary significantly based on things like the length of the prompt, the amount of output generated, the specific model used, even the time of day sometimes. This means you need systems in place to monitor things like token usage very closely. Tokens are kind of the currency of LLMs, and tracking usage helps predict and control those variable costs associated with API calls. You also need to meticulously track inference costs per request type or per specific use case. This allows you to do highly targeted optimization, focusing your efforts on the most expensive operations or features. Without this granular visibility, costs can just spiral completely out of control, potentially wiping out the entire business value the AI was supposed to create. So, pulling all this together really necessitates rigorous evaluation frameworks that go beyond traditional software testing metrics when you're dealing with LLMs in production. You need ways to assess their dynamic data handling capabilities. How well do they cope when the input data changes, when new information becomes available? You can't just test against static, unchanging data sets. You need real-world performance evaluation under varying conditions to identify robustness issues, find those tricky edge cases, and uncover failure modes that would simply never show up in controlled lab testing. Ultimately, all this data, the technical metrics, the quality scores, the user feedback, the cost tracking it all, needs to feed into continuous feedback loops. These loops enable systematic improvement based on actual production experience. Things like segment-specific performance analysis become important, ensuring the system works well not just on average, but for different user groups, different types of queries, different parts of your business. The key balance here, and it's a recurring theme, is combining automated monitoring for scale and efficiency with thoughtful human oversight. Humans need to be involved in reviewing tricky cases, interpreting subjective feedback, making strategic decisions about model updates or retraining, and ensuring the system stays aligned with organizational values and ethical guidelines. You need systems that can adapt and improve, but always with human control and judgment guiding the process.
Okay, given that ROG retrieval augmented generation is often that optimal starting point for most companies, as we discussed, let's zoom in specifically on how to do RAG right. What does a really well-optimized RAG system look like from an architectural standpoint? Because I'm guessing just plugging a basic vector database into an LLM and calling it a day probably isn't going to cut it for serious enterprise scale and performance right.
You are absolutely right. A production-grade RAG system requires really careful, deliberate architectural choices to handle the demands of an enterprise environment, things like high query volumes, low latency expectations, and the need for consistently relevant and accurate information retrieval. It's much more than just connecting two boxes. One of the core elements for an optimized RAG setup involves using distributed vector databases with sophisticated sharding strategies. Vector databases are these specialized databases designed to store and search embeddings, those numerical representations of text data, incredibly quickly. For large enterprise knowledge bases, you need to distribute this database across multiple machines or shards to handle the load and keep search times low. Think of sharding like dividing a massive library catalog into smaller, more manageable sections. Instead of one librarian searching the entire thing, you have multiple librarians working in parallel on their specific sections. But simply splitting the data isn't enough. Effective sharding strategies need to be intelligent. They consider things like document similarity, maybe grouping related documents on the same shard, and common query patterns to minimize the need for slow cross-shard searches. It's about balancing parallel processing with network overhead to get the fastest possible retrieval, even as your data grows.
So it's not just splitting it randomly, but strategically dividing the knowledge to make lookups super efficient. Makes sense. What else?
Next up are GPU-accelerated models and intelligent caching strategies. Running the language model inference, and sometimes even the embedding generation on GPUs is pretty much essential for acceptable performance in production. Beyond raw hardware power, caching is key. You can implement model inference caching, which stores the generated answer for common or identical queries, so you don't have to recompute it every single time. This can dramatically reduce response times for frequent requests. You can also use embedding caches, which store the numerical representations, embeddings of your documents, or maybe even common query phrases. This speeds up the retrieval phase of the RAG process, as you don't have to constantly recalculate these embeddings. Like all caching, though, it's a balancing act. You need to carefully tune these caches, balancing how much memory they consume versus how often you get a cache hit, finding what you need in the cache, to really optimize overall system speed and resource usage. It's like giving your RAG system a really fast short-term memory for common stuff.
And our sources mentioned something really intriguing, this idea of decoupling chunks for retrieval versus synthesis. That sounds quite advanced. What does that actually mean in practice? How does it help?
Yeah, that's a really neat, more advanced optimization technique. It gets into the nuance of how these systems work. It basically means recognizing that the best way to represent a piece of text for finding relevant information in your vector database might be different from the best way to represent it for the language model to understand and use to generate a good answer. For retrieval, maybe you want larger, denser chunks of text that capture broader context, maximizing the chance that your search query will match something relevant. But for synthesis, when the LLM is actually writing the answer, maybe smaller, more focused chunks are better. They might be easier for the model to process accurately and integrate smoothly into a coherent, natural-sounding response without getting overwhelmed by too much surrounding detail. So this decoupling approach allows you to optimize these two stages independently. You prepare your data in two different ways. One optimized for search, one optimized for generation. This can potentially improve both the relevance of the information you find and the quality of the final answer the LLM produces by giving each stage exactly the format it works best with. And finally, especially as your knowledge base gets really large and complex, you need structured retrieval approaches. This means going beyond just simple vector similarity search. You might implement mechanisms like metadata filtering, only search documents tagged HR policy created in the last year, or maybe hierarchical indexing, allowing the system to drill down through topics rather than searching the entire flat space. These techniques help dramatically reduce the search space for specific queries, making retrieval much faster and more accurate, especially for very large document sets. It stops the system from trying to boil the ocean for every single query. Now, this all naturally leads to a critical question. With RGA, you're directly tapping into your organization's own knowledge base, right? What about the quality of that content, the stuff it's actually retrieving? Because, as we keep saying, garbage in. Well, you know the rest. Confidently hallucinated garbage out.
Yeah, I imagine the quality of that retrieval corpus is just as vital as the quality of training data for fine-tuning, maybe even more so, because it's directly feeding the answers in real time.
It's absolutely fundamental. In fact, data quality and meticulous curation strategies for your RG knowledge base are arguably the most critical factors for success. You can have the most sophisticated retrieval algorithms, the fastest vector database, the cleverest prompt engineering, but if the information the system retrieves is outdated, inaccurate, poorly written, or just plain wrong, the output will inevitably be flawed, potentially dangerously so. The key insight from our sources here is often to start with core high-quality content rather than attempting to index entire knowledge bases. Don't just dump every single file from every network drive into the system on day one. That's a recipe for disaster. Instead, focus on careful curation. Identify your most accurate, relevant, up-to-date data sources first. Focus on quality and trustworthiness over sheer volume. A smaller, well-curated knowledge base will almost always produce better, more reliable results than a massive, messy one. It's about precision, not just bulk indexing. Furthermore, you need automated data quality management specifically tailored for this retrieval content, especially at enterprise scale. This means implementing continuous processes to monitor things like content relevance. Is this document still useful? Accuracy and currency, is it up to date? Just like your training data needs ongoing updates, your RAG knowledge base absolutely does too. You need regular content updates, ideally integrated smoothly into your existing content creation and management workflows. This ensures the information the RAG system retrieves stays current and valuable for users, preventing it from becoming a source of stale, misleading, or simply incorrect information. You have to treat your knowledge base as a living, breathing asset that requires constant care and feeding.
Okay, that makes perfect sense. Now, let's shift gears slightly to the topic that looms large over any enterprise technology, especially one dealing with potentially sensitive company data. Security. GenAI systems, they seem to introduce some truly novel challenges here, don't they? It feels like traditional security playbooks just aren't going to be enough for these new kinds of threats.
You're absolutely right, they aren't enough. Our sources are very emphatic about this. Traditional security approaches prove insufficient for addressing the unique attack vectors and data protection requirements that arise in AI deployments. We are genuinely dealing with a new paradigm of potential threats and vulnerabilities. Take access controls, for example. Traditionally, you worry about who can log into a server or access a database. With GenAI, you still have that, but you also have to control who can send queries to your AI model endpoints and API gateways. And critically, you need to think about what kind of queries they should be allowed to send. You need to implement more sophisticated role-based access that considers not just user identity, but also the sensitivity of the queries they're making and the potential impact of the responses the AI might generate. Maybe certain users can only ask general questions, while others can query more sensitive internal data via RM. Plus, these controls need to include things like robust rate limiting to prevent abuse or denial of service attacks where someone just floods the model with requests. You need detailed query logging for auditing and investigating potential incidents. And you need sophisticated anomaly detection systems that can flag unusual patterns of queries that might indicate misuse or an attempted attack. It's a much more dynamic, context-aware level of access control.
Wow, that's a much more fine-grained level of control than many systems have today, almost needing to understand the intent behind the query. And data protection. That must be expanding dramatically, too, given the nature of how these models process and generate language.
It absolutely is. Data protection for GenAI extends far beyond just securing the database where the training or RAG data lives. It involves things like rigorous input validation. This is crucial for preventing those prompt injection attacks we mentioned earlier, where attackers craft malicious inputs designed to trick the model into revealing sensitive information, executing unintended actions, or bypassing safety filters. You also need robust, sensitive data scrubbing. This means automatically identifying and removing or masking personally identifiable information, PII, things like names, addresses, social security numbers, credit card details from both the input prompts and the generated outputs. You absolutely cannot have the model accidentally learning or regurgitating sensitive PII. And of course, strong encryption is vital. Data needs to be encrypted both at rest when it's stored, like training data or model weights, and in transit when queries and responses are moving across networks. This protects the entire data lifecycle involved in AI operations. What's really fascinating here, though, is how much the security focus has to shift to the model itself and its outputs, not just the surrounding infrastructure. Model security presents unique challenges that traditional network or application security frameworks just weren't designed for. For instance, you need prompt filtering capabilities. These act like firewalls specifically for prompts, trying to detect and block those adversarial inputs designed to manipulate the model's behavior or make it say harmful things. You also need effective content moderation on the output side. This ensures that the text generated by the AI meets your organization's standards for appropriateness, safety, brand voice, and also complies with relevant regulations. You don't want your AI generating illegal, hateful, or inappropriate content, and adversarial testing is absolutely critical. This involves proactively and systematically trying to break the model, probing it for vulnerabilities, trying to trick it, finding its failure modes before malicious actors do. It's like having your own internal red team, specifically focused on attacking your AI systems to find weaknesses. You have to actively look for ways it can be misused.
And with all these new layers of security, technical, behavioral, model-focused, I can only imagine the compliance landscape must be an absolute minefield right now, with new regulations probably popping up all the time.
It certainly is a dynamic and complex area. Compliance requirements for GenAI systems often go well beyond those for traditional software. You need to ensure compliance with existing data privacy regulations like GDPR in Europe, CCPA in California, HIPAA for healthcare data, and so on. But you also have to grapple with the rapidly evolving landscape of AI-specific governance requirements and guidelines that are emerging globally. Things like the EU AI Act, various national AI strategies, they're all adding new layers of expectation around transparency, fairness, accountability, and robustness. This is where establishing dedicated AI governance boards becomes really essential for providing that high-level oversight for complex AI initiatives. These boards need truly cross-functional expertise. You need your CISO, Chief Information Security Officer, probably your CDO, Chief Data Officer, or maybe a new CAIO, Chief AI Officer, representatives from legal and compliance, senior engineering leaders, risk management professionals all at the table. This diverse group ensures that AI projects get looked at from all the critical angles: technical feasibility, legal permissibility, business value, operational readiness, security posture, and ethical implications. These governance boards should be responsible for setting clear, organization-wide policies for things like AI system deployment criteria, ongoing monitoring standards, incident response protocols specifically for AI failures, and frameworks for continuous improvement. Their core job is to effectively balance innovation opportunities with risk management, ensuring that AI initiatives align with the organization's values, risk appetite, and the ever-changing regulatory environment. They are essentially the ultimate guardians of responsible AI adoption within the enterprise.
Okay, let's talk brass tacks. Let's be real. None of this amazing technology gets built to run without a budget. And GenAI costs, from everything we hear, can be, well, incredibly tricky and sometimes wildly unpredictable. How do you keep the economics of AI in check? How do you prevent those budgets from just spiraling completely out of control, especially when usage patterns can be so volatile?
Yeah, you're hitting on a major source of anxiety for many organizations dipping their toes into GenAI, and for good reason. Effective GenAI cost management requires really multi-layered strategies precisely because these systems, unlike most traditional software, exhibit highly variable costs. Costs fluctuate significantly based on usage patterns, who's using it, how often, for what the specific models you choose, the complexity of the prompts, the infrastructure you run it on. This inherent unpredictability is a massive management challenge. The absolute bedrock, the foundation of any effective cost optimization effort, has to be detailed monitoring, and I mean really detailed. This requires granular tracking of costs broken down by the specific model being used, by the particular use case or application, and ideally even by user segment or department. This level of visibility is the only way organizations can truly identify the actual cost drivers. It lets you pinpoint specific areas for optimization that would be completely hidden if you only looked at aggregated cloud bills. You need to understand precisely where every dollar or even every fraction of a cent is going and why. You need that microscope.
So it's about getting super granular visibility, seeing the entire financial forest, and identifying all the most expensive trees within it. Okay, once you have that visibility, what about optimizing the models themselves to actually reduce those costs?
That's where techniques like model distillation come in, and it can be a really powerful lever. The basic idea of distillation is you train a smaller, simpler student model to mimic the behavior of a larger, more complex, and usually much more expensive teacher model, specifically for a narrower set of tasks. The goal is to have these smaller, specialized, cheaper to run student models handle the bulk of the simpler, high volume tasks, while you reserve the big, expensive, powerful general purpose models only for the really complex queries that genuinely require their full capabilities. Think of it like an intelligent triage system for your AI workloads. You ensure you're always using the most cost-effective tool that's still capable for the specific job at hand, rather than just defaulting to the biggest hammer, the most expensive model for every single nail. This approach can lead to really significant reductions in overall inference costs, especially at scale. Now, this naturally raises an important question. Beyond just optimizing the models themselves, how can we optimize the underlying infrastructure and even the model training or fine-tuning process to save costs? Because these models have to run somewhere, they need data, they need compute power, and none of that hardware or cloud infrastructure is free, right?
Exactly. Those GPU hours, they add up incredibly fast.
They really do. So infrastructure optimization is absolutely key. This involves meticulously tailoring your infrastructure, whether it's on-prem or in the cloud, to match the specific, often demanding requirements of your GenAI workloads without overspending. This means things like right-sizing your GPU instances. Don't pay for more GPU power than you actually need for a given workload. Maybe you can use smaller instances for some tasks or schedule workloads to take advantage of cheaper spot instances if appropriate. It also means optimizing storage, figuring out the most cost-effective way to store massive model weights, huge training data sets, and potentially large vector databases for ARGA. And it involves carefully planning network capacity to handle the potentially high throughput needed for real-time inference without creating bottlenecks or incurring excessive data transfer costs. It's about being incredibly efficient and precise with all your physical and virtual resources, constantly looking for ways to eliminate waste. Another really important technique on the model customization side is parameter-efficient fine-tuning, or PEFT. We touched on fine-tuning earlier as being resource-intensive. PEFT methods are a way to get many of the benefits of fine-tuning, customizing a model for your specific needs, but with significantly reduced computational and storage costs. Think of it like tuning a car's engine, not by completely rebuilding it, but by cleverly adjusting just a few critical components or adding a small, efficient turbocharger. PEFT approaches typically work by freezing most of the large pre-trained model's weights and only modifying a small subset of parameters, or perhaps adding a few small new layers that get trained. This means they can achieve substantial customization and performance improvements using only a fraction of the compute resources, memory, and time required for traditional, full fine-tuning. This is a real game changer, making model customization much more accessible and affordable for a much wider range of organizations and use cases. And finally, you need smart workload distribution strategies, especially in cloud environments. This involves implementing things like dynamic resource allocation and auto-scaling systems that can automatically match your infrastructure capacity to the fluctuating demand patterns of your AI applications. This means your infrastructure can scale up almost instantly when usage surges, ensuring good performance, but then crucially, it can also scale down efficiently and automatically when demand is low, saving you significant costs during off-peak hours or quiet periods. However, these auto-scaling strategies also need to be sophisticated enough to account for things like the startup time required for loading large language models into memory. It's not instantaneous, and they need to manage the considerable memory requirements for maintaining model state across multiple user requests. It's a continuous balancing act, ensuring optimal performance and availability without incurring excessive unnecessary infrastructure costs due to idle resources.
Okay, wow. These technical strategies, architecture, data, security, ops, cost optimization, they're all incredibly important. But ultimately, who's actually doing all this complex work? What are the new skills organizations desperately need to build, both in their tech teams and maybe even more broadly, to truly succeed with GenAI in this new era?
That's such a critical point, and honestly, it's one that organizations frequently underestimate, leading to major bottlenecks in stalled projects. Our sources consistently emphasize that successful GenAI implementation requires specialized skills that extend far beyond traditional software development. It's just not the same game anymore. It's not just about writing code. It demands a deeper, more intuitive understanding of these new, complex, often probabilistic systems. And importantly, it's not just the technical folks. Business stakeholders also need to develop a much better understanding of what these AI systems can realistically do, what their limitations are, so they can make informed strategic decisions and partner effectively with the technical teams. Otherwise, you get misaligned expectations and wasted effort.
So, focusing on the technical teams first, what are the absolute must-have skills they need to be prioritizing, acquiring, or developing right now? Is it just about learning Python libraries, or is it something much deeper than that?
Oh, it's definitely much deeper than just learning specific libraries, although that's part of it. Technical staff need focused, often hands-on, training in several key areas that are quite different from traditional software engineering. This includes model selection methodologies. How do you actually choose the right model, proprietary or open source, big or small, for a specific task, considering that complex trade-off between performance, cost, data needs, security constraints, and operational complexity? It's about making smart, data-driven choices, not just grabbing the latest model off the shelf. Then there are prompt engineering skills. We talked about this as an architectural pattern, but it's also a crucial skill. Being able to effectively craft prompts to guide the model's behavior and optimize its output without having to resort to expensive fine-tuning is incredibly valuable. It allows for rapid iteration and adjustment. ARA implementation expertise is also increasingly vital. This covers understanding the different architectural patterns for ARGI, the specific data preparation techniques needed for retrieval corpora, vector database management, and the operational practices for keeping ARGI systems running reliably and accurately. And finally, they need strong LLM-Ops capabilities. This is essentially the specialized field of operations tailored specifically for large language models. Think of it as DevOps, but adapted for the unique challenges of AI systems. It encompasses the specialized monitoring, evaluation techniques, versioning, deployment strategies, and optimization practices that are specific to managing language models in production, which we've discussed quite a bit. Now, what's truly fascinating here, and maybe even more important in the long run, is that it's not just about the technical team acquiring these deep skills, it's about the entire organization developing a more realistic, more sophisticated understanding of AI. This is why cross-functional training is so incredibly important. You need programs that help business stakeholders, product managers, marketers, legal teams, executives develop realistic expectations for what AI can actually achieve. They also need to understand the inherent limitations, the potential failure modes, the ethical considerations, the data requirements. This broader organizational literacy helps prevent two big problems. One, overinvestment in inappropriate use cases where AI simply isn't the right tool or the value isn't there. And two, critically, underinvestment in areas where GenAI could actually deliver truly significant game-changing strategic value, perhaps because the potential wasn't fully understood. It helps close that gap between business vision and technical reality, fostering much more collaborative and informed decision-making.
So the goal isn't just to build an AI engineering team, it's really to build an AI literate organization. top to bottom.
Precisely. And because this field is just evolving at such a breakneck speed, new models, new techniques, new security threats, new regulations emerging seemingly every week, continuous learning programs become not just beneficial, but absolutely essential for survival. Organizations simply must establish ongoing education and skill-building initiatives. These need to keep their technical teams current with the latest developments, sure, but also continually deepen the expertise and the foundational concepts that underpin AI. It's a marathon of learning, not a one-time sprint. You have to build a culture of continuous learning around AI. And the most effective way people actually learn these complex GenAI skills, it consistently comes from practical application, from getting hands-on experience with real-world, albeit maybe small-scale, projects. Organizations should actively prioritize creating opportunities for their team members to experiment with AI systems, to build things, to break things in controlled, low-risk environments before they're tasked with building and managing high-stakes production deployments. It's all about learning by doing, safely, and building that practical intuition before deploying into the wild where mistakes can be costly.
Okay, this is great. So let's imagine we have all these crucial pieces falling into place. We've got the clear strategy, the right architecture decided, the data is clean and governed, the teams are skilled and learning. Now, how do we actually run the implementation project itself? Is it just like managing any other complex software project using standard methodologies? Or is there a different rhythm, a different approach that works better for the inherent uncertainty and experimental nature of GenAI?
It's definitely a different rhythm, one that needs to embrace complexity and uncertainty, not try to eliminate it up front, which is often the goal in traditional project management. Our sources strongly, almost universally, advocate for iterative development cycles. These prove absolutely essential for managing the kind of inherent complexity and, frankly, unpredictability that comes with GenAI implementations. Unlike many traditional software projects where you can often define requirements quite completely at the beginning and then just execute a linear plan, AI projects, almost by definition, require ongoing experimentation, discovery, and continuous refinement. You learn about the system's true capabilities, its surprising limitations, and the best ways to optimize it through practical, real-world interaction and observation. You have to plan to iterate, to learn as you go, and constantly improve the system based on what you find. Expecting to get it perfect on the first try is usually unrealistic.
So definitely not a big bang launch approach then. It's much more like a series of smaller controlled experiments or releases that build on each other over time.
Exactly. That's precisely why starting with pilot projects in controlled environments is so highly recommended. It allows your teams to gain that invaluable hands-on experience, to test specific hypotheses about value or feasibility, and to gather critical performance data and user feedback, all while limiting the potential blast radius and cost if things go wrong early on, which they sometimes do. These pilot projects should ideally focus on very well-defined, relatively narrow use cases. They need clear success criteria. What does good look like for this pilot? And importantly, they need specific stakeholder groups who are genuinely invested in the outcome and willing to provide meaningful, actionable feedback on everything from the system's performance and output quality to its actual usability in their daily workflow. You get those crucial real-world insights quickly and safely without putting the whole enterprise or your reputation at risk right away. It's all about learning to walk before you try to run a marathon, and learning from every single step, even the missteps. Now, this raises a really important follow-up question. How do we make sure that these pilots and these iterative cycles actually lead somewhat useful? How do we ensure they result in a system that continuously improves and delivers value, rather than just becoming an endless cycle of tweaking without clear direction or tangible progress?
Right. It sounds like feedback must be absolutely central to this working, not just looking at the technical metrics, but really listening to the people involved.
It absolutely is. Collecting stakeholder feedback and doing it continuously throughout the entire development and deployment lifecycle is completely non-negotiable for success. It's that crucial human element that ensures the technical capabilities you're building actually align with real-world needs, user workflows, and expectations. And this feedback needs to go beyond just the basic functional requirements. Does it technically do the thing it's supposed to do? It must also cover critical aspects like usability. Is it easy and intuitive to interact with? Reliability, does it consistently work when needed? And integration concerns how well does it fit into existing tools and processes. A technically brilliant AI system that users find confusing, unreliable, or difficult to integrate into their jobs simply won't get adopted and therefore won't deliver value. Their input is absolute gold. Beyond soliciting direct user feedback, conducting systematic output analysis is also key. This is where you or your team actively look at samples of what the AI is actually producing over time, not just relying on what users report. This helps you spot more subtle patterns of errors, maybe emerging biases, recurring types of hallucinations, or areas of inefficiency that might not be immediately obvious from just casual interaction or aggregated metrics. You need to inspect the output regularly. All of this, the performance metrics, the cost tracking, the direct user feedback, the systematic output analysis, needs to feed into building comprehensive feedback loops. These create robust systems and processes that enable the continuous monitoring, evaluation, and optimization of your AI's performance over its entire lifespan. Such loops should track those key performance metrics we discussed earlier, making sure they're correlated with actual quality measures. They should include regular reviews of system behavior involving both technical experts and end users. They should facilitate systematic experimentation with different model versions, prompt strategies, or IRG configurations. And crucially, they should help foster organizational cultures that value both operational efficiency and ongoing innovation and learning in the AI space. The key balance, as always, comes back to blending automated monitoring for scale and detection with thoughtful human oversight for interpretation, judgment, and strategic decision-making. This ensures that your AI systems can adapt and improve based on real-world data, while humans remain firmly in control of critical decision, ethical considerations, and maintaining alignment with overall organizational values and strategic goals.
So wrapping this all up, what does this really mean for you, our listener? We've taken a seriously deep dive today into the complexities, the challenges, and the strategies required to get generative AI working effectively, reliably, and responsibly within an enterprise setting. It's crystal clear this isn't just another technology project. It's a profound technical and organizational challenge that really touches almost every part of a modern business. The core message, the big takeaway from all our research, seems to be that the transformation from a GenAI proof of concept to truly production-ready systems represents a significant technical and organizational challenge. It really fundamentally requires treating GenAI as a complex system needing dedicated resources, specialized governance, and continuous optimization, not just deploying a model and hoping for the best. For you, the listener, the undeniable implication here is that those organizations that truly commit to mastering these foundational elements, the ones that position themselves with a clear strategic vision, make smart, robust architectural choices, establish comprehensive operational and governance practices, and foster a deep commitment to continuous learning and adaptation. Those organizations will find themselves uniquely positioned. They'll be the ones realizing significant, tangible, undeniable competitive advantages from their GenAI investments. It's really about building that solid, intelligent groundwork now, not just chasing the fleeting hype.
And this really raises one final important question for you to consider as you navigate this incredibly fast-moving landscape. In a field like GenAI, where today's cutting-edge best practices will undoubtedly evolve, perhaps even radically by tomorrow, what single characteristic, what single trait is arguably the most critical for ensuring long-term success? It's tempting, I think, to get completely caught up in the specific technical details, the latest model architecture, the newest vector database, the cleverest prompt hack. But the reality is all of those specifics will change probably faster than we can imagine. The sheer technical complexity we've discussed today shouldn't discourage you from adopting GenAI. Instead, it should motivate you to engage in really thorough preparation, to adopt systematic, iterative implementation approaches, and to focus on building sustainable, adaptable AI capabilities over time, not just one-off projects. Ultimately, your organization's adaptability, its profound commitment to continuous learning, and its fundamental willingness to rigorously adjust strategy and execution based on new data, new insights, and real-world feedback. These qualities are likely just as important, if not more so, than any specific technical implementation choice you make today. That inherent flexibility, that deep-seated culture of learning and iterating, that's what will truly define lasting success in this incredibly dynamic, undeniably transformative landscape of generative AI.